Welcome to the 19th chapter on verified models and verified runtime validation in the Logical Foundations of Cyber-Physical Systems textbook. This chapter provides an important twist on cyber-physical systems analysis. Now, without any doubt, formal verification provides extremely crucial safety information for cyber-physical systems with an absolutely exhaustive coverage of all the infinitely many possible behaviors that you couldn't ever cover with any amount of finite testing. The catch is that the safety results then cover all the behavior of the verified CPS models, but those guarantees only provide safety guarantees to the actual CPS implementation to the extent that this implementation actually fits the model. And obtaining good enough models of physics is rather a non-trivial challenge in and of itself. In this chapter, we will look at ways of systematically transferring safety guarantees about a CPS model to safety guarantees about the actual implementation. We will be using provably correct runtime compliance monitors. And when you run those monitors in an actual CPS implementation, then these monitors validate the actual execution of the system in a verified way against the verified models that were previously proved safe and thus save themselves. Now, the tricky bit is that, of course, in order to have full coverage of safety for all possible behaviors, it is rather necessary to provide a model of the system under scrutiny, because that model is not just a model of the controls parts of it, but also it does have to include the relevant parts of physics. This is kind of sort of challenging. Models of reality come with certain inevitable challenges. The world is a complicated place, which implies that our models of the world will either also be extremely complex or focus on certain simpler fragments. If they're extremely complex, well, then we probably will fail to exhaustively analyze them in proofs. If they focus on simpler aspects of it, then there's the question, did we do so faithfully compared to reality? And the point is, of course, that oftentimes do we very much want to work with simplifying abstractions in our models to make the descriptions easier. Just think back of the bouncing ball. We didn't really literally explain in a whole lot of detail how exactly and in what way the bouncing ball bounces back from the ground. We just described that it did, and maybe with even different damping coefficients applied to it. And, well, that model then included a lot of behavior that was physically unreal, but also the behavior that we observe in physics. And since it was a lot easier to model that and also analyze it, that gave us a much easier verification result for bouncing balls. Now, when we're done with the proof of safety, we have proof that the model is safe, but it only verifies the actual CPS implementation to the extent that this implementation fits the model. And then that begs the question how the model's safety result transferred to the safety of the actual implementation. As we've already discussed in part 1 of the textbook, we can't literally put in an actual physical robot or an actual self-driving car into a logical modality and prove stuff about it, because even if that gives us a lot of detail about the mechanics of the system, we still have to have a model of the physical motion, for example, and the behavior of the environment. So we have to live with models and deal with them. So instead, what we'll do in order to transfer the safety guarantees about models into safety reality is we will generate monitor programs that you can run in the actual CPS implementation that check it all the time whether the behavior fits with what the model of the safety proof assumed would happen. And these monitors are then also accompanied by a proof of correctness that they say will perform all this checking in a provably correct way, so that whenever they say everything is fine, this behavior is really safe. So indeed, what we will be learning today from a modeling and control side has come to realize the inevitable differences between models compared to reality, because it's either infeasible or even completely impossible to model all the complexities of reality exactly. But fortunately, that's not even necessary to model all of reality to make predictions about the particular cyber-physical system affecting only a part of the world. But then, of course, we somehow have to make sure that we model that part of the world in a sufficiently correct way, which brings up the model compliance questions. In a little bit, we'll also look at the implications for architectural design principles this observation has. Today's lecture is again big on computational thinking because the relationship between truth and proof are of absolutely fundamental significance in logic and are essentially the backbone of soundness and completeness considerations, but they also enable us to distinguish having a proof in a model versus the truth in reality. And by having proved a lot of properties about models of cyber-physical systems, does logic give us the way of relating the proofs in those models to the real truth in the real reality, where we carefully need to trace assumptions to make this work. And of course, for cyber-physical systems, the daunting task of finding models doesn't only involve the models of the controls, but in particular the model of physics. And people in physics have been coming out with models of reality for centuries with increasing success. And the point is that this problem is fundamental and we can't overcome it by merely declaring that we shift to more precise models, because even more precise models of reality are just that, more precise models of reality. Now, seemingly, you might be able to sidestep what we're talking about in today's lecture by instead working with CPS data and experiments, but issue is that those have absolutely no predictive power without again assuming some corresponding model of reality that relates what was observed in the data recorded to what will be observed in similar situations, which still leads to the vicious cycle of assumptions either way. So instead, what we'll be doing is turning provers upside down, which you might want to have done in any case whenever a proof didn't quite work out, but today we'll turn the prover upside down for another good reason, and look at correct by construction principles for the actual systems and their monitors, and then relate the statically verified safety theorems to dynamic contact checking of monitors in provably correct ways in order to enable proofs for the actual CPS implementations, despite the fact that this is a rather subtle problem. On the CPS skill side, this lecture is of fundamental importance in order to make it possible to tame the CPS complexity, because it provides ways of isolating the safety critical parts of the system and not have to worry about the rest, yet still have a very disciplined argument about the overall working principles of the system, so that you can simplify models without losing the connection to real CPSs, which is a very beneficial aspect. By combining offline verification with online verification and runtime validation of the system using online monitoring, such that you overall combine static, once ahead of time predictions with the actual physical run of the system. Well, let's get started. Let's first understand the fundamental challenges with inevitable models. Imagine you've proved in differential dynamic logic the safety of a system, that whenever you start in a state where the formula A is true, then all behavior of a system model that repeatedly will first run the control and then the planned, no matter how often it has done that, still the system is safe no matter what. That's of course an extremely strong, compelling thing to write home about, that this is proved. But what else could possibly go wrong even if you have a proof of safety like that? Well, you could have proved this property but wrote down the wrong question. So what happens, for example, when your safety condition, the post condition S, is wrong? Well, I guess in that case, you have a beautiful proof for the wrong question, because you proved maybe that your car never exceeds the speeding limit, but forgot to prove that it also doesn't crash with others. Or the other way around. Maybe you prove that your car never crashes with others, but it does so by exceedingly speeding up, and that's probably also not a great idea. In other words, we very carefully need to review to make sure that we're really asking the right question. what if the precondition A is wrong? Well, in a sense, that's less bad, right? Because at least we cannot have forgotten any required assumptions in A, because the proof would have rescued us. The proof simply wouldn't have worked had we forgotten something in A. But there's still a catch, because in our process of trying to find out the appropriate initial conditions that make this property true, maybe we overshot the goal. Maybe we've been assuming too much, things that narrow the scope of where we know the safety of the system too much, which means if you try to turn the system on, it'll simply be too picky and say, sorry, no, the conditions aren't met, I'm not running today, even though in principle we could have shown safety for those cases as well. But inappropriate preconditions are already not quite as bad as inappropriate postconditions. Well, that's a cheerful thought. What if the control is wrong? Well, I guess we should have written down a better controller model. But still, of course, there's a good reason for differences between controller models versus the actual controller implementations. Like, in principle, you could put in every detail about the control implementation as a control model and then verify that. But on the other hand, of course, abstraction that we're doing in the controller model can also be highly beneficial to simplify the analysis. And besides, then we don't need to re-verify every time we change anything at all in the implementation. Just think of, a car controller that may be speeding up or slowing down as a function of distances to other vehicles, and as a function of how fast you're going, as a function of what the fuel efficiency is like. And all of these are, of course, really important in an actual implementation, but not all of those aspects are really safety critical, so not all of those need to be included in a model. That often is easier when we work with a little bit more non-determinism in it. And that, of course, this non-determinism is not exactly what we want in the actual behavior of the system at the end of the day. Now, what if the plant is wrong? Then we're kind of toast. That would be bad, right? If you write down a model for a bouncing ball, prove it in ChimeraX, and then rename the file to safe awesome space rocket.chimerax, well, I'm glad it has a proof, but it's a proof with completely wrong dynamics, because bouncing balls and space rockets aren't quite the same thing. So it's important that we get the plant model right. And that's, of course, where a lot of the subtlety starts, because the plant needs to describe the real physics, and real physics is not trivial. So in other words, these models are absolutely inevitable, but George Bock said that even if all models are wrong, some models are useful. And that's a cheerful thought, because indeed, that's kind of the right attitude. It's not possible to write down every little detail about all of physical reality and then try and do a safety analysis for it. For example, right, maybe you should have written down a model that is more precise by including Schrödinger's equations of quantum mechanics. Well, that is a more precise model of physics, but not only is it still a model of physics, but it's also kind of the wrong one for the prediction of the motion of cars, because quantum mechanics is much more important for small particles, and cars aren't that small. Likewise, maybe you could have gone to relativistic dynamics, Einstein mechanics, right? That's also all right, but that's a more precise model of physics, but one that's really only relevant for particles that are moving very quickly, and the speed of light is usually not quite allowed for cars in most places. And also, when you're trying to understand the safe motion of the car, even if you stay within Newtonian physics, have you really modeled the effect of the turbulence on the windshield wiper correctly? Probably not, but you also shouldn't if you would like to predict whether the car controllers are safely speeding up and safely slowing down. So the point is, under all of those circumstances, is it actually important and beneficial to identify the appropriate model? And of course, models absolutely are needed in order to enable any predictions about the future at all. But you need to identify the right models. Now, why do we need those models to enable predictions? Couldn't we just try it out and measure and collect data? Of course we can, of course we should, but it doesn't overcome the models question, because if you wrote down a big table where you recorded position and velocity and steering angle, and whether the car's motion was safe, that is a great idea. Please do it, but it won't exactly overcome the question, what happens if you were to do that again? Maybe, for example, you recorded the motion with 100 kilometers an hour. That was safe, so you feel compelled to do that again, but of course it may not be a great idea tomorrow when there's a lot more traffic on the road. Or maybe you've recorded all of that, even the traffic situation, wrote all of this down, but that still doesn't give you the license to predict that it's going to be the exact same thing again tomorrow without having a model of a relationship of the recorded data to other situations, because, well, maybe the slope of the track is completely different and the behavior of the car will be different. You didn't record that. Or maybe all of a sudden there's ice on the road and you haven't had that last week. So you still need to relate this. And what happens, is it independent of the altitude where the car is going? Probably. Well, except that at very high altitude is the level of oxygen in the air different. So all of a sudden the behavior of your engine might be a little bit different. So the point is that all of these are true, and you still need models to overcome those discrepancies. So models are absolutely inevitable, but at the same time, is it not necessarily helpful to go for the most elaborate models to predict behavior of reality? Indeed, we now understand the challenge that verification results about models, of course, only apply if the CPS fits the model, which leads us to investigate verifiably correct runtime model validation to make up for this difference between models and reality. And once and for all, cut through this Gordian knot of vicious circles of models assuming models assuming models, using a technique that's called Modelplex. By runtime monitoring. So if we have proved such a formula, how could we use runtime monitors in order to establish whether these assumptions that are in the model are satisfied in reality? Well, how can we model the precondition, for example? Well, I guess the precondition would include assumptions such as, is the current distance to the car in front of us big enough? And are we presently going with velocity 0? And maybe do the brakes work? So we can check all of those. The assumption that we can measure the quantities involved, we can literally go down the checklist, like a pilot, for example, goes down the checklist when they're on the runway before they take off, whether everything is really fine. And if it isn't, we just veto the activation of the cyber-physical system and say, sorry, something's wrong, you don't get to turn your robot on, for example. That was good. How do we monitor the post-condition? Well, I guess we could evaluate it similarly and just check in reality whether the safety condition is satisfied. But if it is, I guess we feel good about it. But if it isn't, we have a problem because it's too late. The system was already unsafe. So just think of this. If your post condition is, I always want my car to be at least 1 inch away from the car in front of it, well, great. And if you have a proof of that, amazing. But if you measure this and say, oops, it looks like we're less than 1 inch away from the car in front of us, even if you notice this in monitoring, it's already kind of too late. And then you can say 1 inch was the wrong number. Maybe it should have been a meter away from another car, but this is the same problem all over again. If you monitor that you're all of a sudden closer than a meter to the car in front of you, but you're already traveling at 500 kilometers an hour, you're trapped in your own physics. You can no longer respond. The phenomenon is that if you can't do anything about it anyhow, maybe you shouldn't be monitoring it like so. It's too late. We need to monitor something else for this to be helpful. So let's move down the list. How do we monitor a controller model? Well, there will be a real controller implementation, which of course will be reading some sensor data, think about what to do, and send the decision off to the actuators. Now there's the question, except for the number of letters. Is this controller and that control model, are they somehow related? Well, we talked about it. We could almost take this thing exactly copy-pasted in there, but then we would run into scalability limits in our analysis of it. Instead, we can run the real controller implementation. It will decide, but before we really execute the decision, will we inspect with the compliance monitor whether the decision that the controller implementation reached was compatible with one that the controller model accepted as possible given the current standard information. And only if we pass muster under this compatibility do we actually send it off to the actuators. Otherwise, we override it, veto it, and decide on something else instead. So think of it this way. If the controller implementation says, I really want to speed up a lot and do a sharp left turn, if that hasn't been verified to be safe in the control model, then we could overwrite this and say, sorry, you don't get to do that. Maybe, slow down a little bit and don't steer quite so hard, and then run this to the actuators instead. That was still quite powerful, actually. So how do we monitor the plant? Ooh, that's somehow difficult, right? Because we can, of course, stare at the, say, differential equations in the plant model and feel good about it, but then in reality, we can observe what physics does to us. The problem with the physics is that there's no source code for the physics. We're stuck with observing what reality did to us and then compare notes and see whether the old sensor data compared to the new sensor data, whether that transition is compatible with one of the things that our plant model predicted. And one of the things is actually a key word in it, right? Just like in the controller, the model may be non-deterministic, permit multiple actions, where the actual control implementation will always choose one of them. So among all of the predictions that were done, do we just need to check that the one that was chosen is one of the permitted ones, so one of the ones that we already know is safe? Likewise, our differential equation might predict multiple behaviors. Wait. Differential equations are essentially unique solutions. Well, that's right, but we might still follow this differential equation for a certain slightly non-deterministic amount of time. So follow this for long or for shorter, and we don't know exactly how long it takes until we get new sensor data in, or maybe there's a disturbance in the actuation of the differential equation, and then we have a slightly different prediction. And as long as we make sure that this prediction is compatible with what really happened, everything is right. What if it's not? We can't just overwrite it as we did in the controller case, say, thank you for this control decision, but no thank you, we're going to do something else, because, well, the real world already evolved. But we can still at least notice this and veto to trigger a best fallback action and say, apparently things are really not working as we predicted the world should be. We've noticed it right away, and we'll mitigate safety concerns by, for example, emergency braking, alerting a human to take over, things like that. But of course, all those monitors that we're running in all those circumstances still had better be correct, otherwise they're not useful or misleading us in our safety judgment, which means that we need verified runtime validation to make sure that we're monitoring in provably correct ways. And what's most subtle about it, of course, the monitors had better be equipped with a safety result ahead of time that tells us ahead of time that when we run a car with those monitors, all of their behavior will always be happy and not, I'll tell you later whether it will be fine or not, which is not super helpful. So that's where Modelplex comes in. It's a technique for verified runtime validation of models by ensuring that the verification results about models actually apply to the CPS implementation. For example, if you have a real system, think of an aircraft, and last time you looked, it was flying north, and the next time you measure, say, it's flying northeast. Now, you have such an observed change of the system, and the question is, my model had its state transition from the old state I-1 to the new state I, and is the real observed change compatible with what the model predicted? In other words, is the model adequate for what reality did to us? And that will be monitored by the model monitor. But within one of those transitions from an old state to the new state, can we actually do a little bit better also? Because after running an actual control implementation, which maybe gives a turn signal or so, can we already ask, before we schedule this for execution, is this compatible with the behavior that the control model allowed? So is the control decision currently safe, and only if so do we schedule it for execution, otherwise we veto it. And for example, when the plant is running, we can also do a little bit better and predict even under disturbance of the plant, right? So given the current control decision that came out from a validated controller, is this safe even under all the possible perturbations and disturbances that the reality might have in store for us, and predict, is it going to be fine until the next cycle? Only then do we actually run it, otherwise we take a more conservative fallback action. And we'll talk about this, the control, and the prediction monitor one step at a time. With the main insights being that verification results about models transfer to the CPS when validating model compliance. And this compliance with models is actually characterizable in logic. I'm sure you can guess it's differential naming logic for the job. And compliance formulas can then be transformed by a proof into a monitor, which gives us a correct by construction verified runtime model validation approach. So first, about model compliance. Zooming into the question, if the reality made a change, is this compatible with one of the things the model could have predicted? So the question is the present CPS behavior included in the model, where of course you will have a sequence of observations, and overall the question for all of those, did this change fit to the model or did it not? And of course, the reason you want to do this at every moment is because you would like to detect non-compliance as soon as possible in order to initiate any veto or fallback actions while you're still safe, as opposed to after you landed you said there was a problem 5 hours ago. Maybe you should have acted then. So the model describes the behavior, but at runtime we only get sampled observations from the system, so we need to transform the model into an observation monitor. Let's do so by looking back at our familiar bouncing ball model for quantum, the bouncing ball, who proved that he can bounce around safely. There's this model from lecture 7. So if you want to monitor this model, there's multiple parts to it, differential equation and control. Let's first only worry about the control and monitor the control behavior. The controller will go from old position and velocity to new position and velocity, and we'll have to develop a logical formula that tells us which change from old data to new data is compatible with what this controller said. And that's actually very easy, right? This controller has two behaviors that are combined by non-deterministic choice. So I guess if we want to develop a logical formula for the job, we turn this into a disjunction that says, there's two behaviors, the ones where we happen to be on the ground, and our new velocity is the negative damping coefficient applied to the old velocity, or we're above ground, right? And then the velocity, the new one, is identical to the old one. And in any case, it's please the position identical to the old one, because this discrete controller doesn't change the position. Why did I write x positive when here it says x not equal 0? Well, because the ODE's the evolution domain constraint says, but we gotta be above ground while we're bouncing around. So if we're above ground but apparently not on the ground, we have to have been at a positive altitude. Now, how do we now monitor reality, whether it is compatible with the differential equation of gravity that the bouncing ball is flying through? Again, we'll need a formula that's talking about the relationship between old position velocity and new position velocity, but there's a lot more choices in there, namely how long the reality follows this differential equation. And remember, the solution of the differential equation would, for example, be that the new position is the old position minus gravity time, and the new position is the old position plus old velocity time minus half gravity times square. But for what time are we talking about? Well, in this model, is there no differential equation for time? So time is unobservable, but we also shouldn't talk about time in the monitor. That means overall the question is there a joint time that explains both the change of the velocity and the change of the position? Now we do have a logical formula with a quantifier in it, but that, even if it would be a correct monitor, isn't a very useful monitor, because if you try and run it in reality, well, we have the question, well, is there such a time such that? And then we'll sit there and say, oh, which time is it? Is it like half a second or 0.952 seconds, or run quantitative elimination to find out? All of that is too slow. Instead, we want a criterion that directly just looking at the velocity and position tells us whether that change is possible under the differential equation. And of course, we've essentially done so already when we're doing the safety proof, because we worried about the invariance for the differential equation. Here it is, and by slight changes of initial height, actual position, whereas actual velocity, and then in this invariant that we start from initial velocity 0. So that, with some notational changes, will lead us over to this plant monitor that will accept certain changes of old and new position and old and new velocity. But this is now permitting too much change, because even if it is an invariant of the differential equation, the differential equation is more specific than this invariant set that we used to the proof. For example, this one doesn't know that time was also always evolving forward in the differential equation, so we need to include this directionality as well by, for example, saying that because of gravity pulling on the bouncing ball, is the new velocity always going to be less or equal the old velocity? The magnitude might have increased, right? But still, in less or equal comparison, will the new velocity always be less than the old velocity because gravity is pulling it downwards? And even that isn't quite enough, because we've now correctly understood in logical form the change that this differential equation can do, but there's still the evolution domain constraint left to be worried about. How do we render this in logic? Well, we could do so by checking that at all intermediate times was this true, but that again would give us a universal quantifier, which isn't very good. Instead, we check that we started above ground and we ended above ground, and because of the monotonicity property of this differential equation and its characterization here, will this imply that we must have been above ground always in between? So now we have a monitor for that, but how do we get a monitor for the entire model that includes both the differential equation and the control part of it? Well, I guess what we have to do is somehow staple the monitors together, the controller monitor with the plant monitor. And here we go, here's the answer. I guess this now gets a little subtle, but here's the point, right? This is the plant monitor, which is showing up in multiple parts here, multiplied in funny ways by damping coefficients or squares of that. Where does that come from? Well, from the control monitor, where we said position was above ground, which means the new position after having run this mix is above ground, and the ODE dynamics monitor was satisfied. Or it was the other case where we ended up on the ground, right? And so that's where we end up at the very end anyhow. And then this ODE monitor works like that, except of course, well, the relationship between the new velocity at the end is still a negative damping coefficient applied to whatever we got out here, which explains the sign flip and the negative c, and here the squares of the damping coefficients. In any case, the point is, these are the monitors, and you can even prove that this monitor is perfect. It detects all runs of this differential equation, if and only if. But the point is, they're kind of sort of subtle and in desperate need of correctness proofs, because we shouldn't just be conjecturing them, we should actually prove them correct, and maybe better yet, synthesize these controllers also correctly, which of course always begs the question, if a monitor fails, in a sense no harm done, because, well, in the worst case it's a false alarm of safety, but if the monitor succeeds, then it had better have a proof that the real behavior of the real system must have been safe. The monitors can fail too often, but they really shouldn't be passing, other than in safe cases. So let's get systematic about it and develop provably correct monitor synthesis. The first question is, of course, well, such a change of reality, how do we know and characterize and logically whether that's compatible with what the model predicted, or at least with one of the things that the model predicted? When are two states linked through a run of a model? So if the old state is called omega and the new state is called mu, then the question whether from this old state that we observed, could we have come to the new state that we've observed, is that compatible with the model alpha? And as the answer, whether the old state omega and the new state nu, whether that pair is in the reachability relation induced by the hybrid program alpha, which we already defined in the first part of the textbook. So, and if you then characterize the prior state information by the variable names x and then posterior state information by the variables x plus, and then this semantical criterion, which is perfectly correct, but in the semantic level, so hard to teach to a computer, can be rendered directly in logic and differential dynamic logic by saying that's true if and only if there is a run of the model alpha with the diamond modality to a state where the values x that have come out by having run the model are equal to the values that the x plus variables hold for this pair of states. So is there a run of alpha to a state where x then equals x plus? And this is a bit of a funky thing that I'm doing here. I'm passing in two states into a satisfaction question for a logical formula, but what I mean by this notation mainly is the same as the old state omega, except that the values of the x plus variable, which didn't occur previously, are modified to the values that in the new state, nu, the variables x have. In other words, here in this state, will x plus assume the value that x has in the new state, and because x plus isn't changing while alpha's model is running, that means at the end will this still precisely have the value that the values of x apparently have gotten to. And because there is a transition from the old state omega to the new state nu in the semantics of the model, if and only if this pair of states, rendered like so, is a signal state, satisfy the differential dynamic logic formula that there is a run of alpha to a state where x equals then x plus. Okay, well that's actually cheerful, right? We have one logical formula, a syntactic piece of information that tells us in an if and only if way whether the transition in reality was compatible with the model. That's good. The only downside is, of course, that even if this is the correct answer for the question which logical formula we should ask for a monitor, it is also kind of a difficult one, right? Because it does still involve the entire model alpha, and the model alpha might not just involve non-determinisms where we have the question which path did the system model have to take in order to explain what the state change with alpha did, and it might involve differential equations, and so that's all difficult to ask, is this formula true or not in real time, right? Because a runtime monitor shouldn't be taking too long. So, no problem. What we now do is take this logical formula, feed it into the Chimera X theorem improver, and ask it to prove it, which it will not be able to do, right? Because there is no proof that we can go to a new state characterized by x plus about which we don't know a thing. The whole point is that we ultimately plug in values for it. So proof of it will fail, and usually when a proof doesn't succeed, you end up with a lot of long faces. In this case, no, you say, well, that's brilliant, because whatever simple arithmetic logical formulas will come out of the proof, having run over it at the end of the day, they will still talk about the old and the new variables, and if we now cannot prove them, but check them at runtime. So we fill in the proof for these arithmetic questions at runtime while the system is running, then we overall have a proof of compatibility of the system behavior with the system model, and thus, because of all the system model behavior having been proved safe, we have a chance to get the actual behavior of the system safe. Now, one of the problems is that this behavior that the two are equivalent will happen if every proof step was an equivalence transformation, but some are not, right? Some are just implications. Now, fortunately, the resulting premises, unfortunately written down here to confuse you, compared to the original conclusion, the premises will imply the conclusion, which means the implication goes this way, which fortunately is precisely the right direction for the correctness of the monitors. If the monitor formula implies the monitor criterion, then we also still know that the observed run is compatible with the model. And here we staple the argument together. If we start with a differential limiting logic proof that if we start in A, then all the model behaviors are safe, then, well, what we do is think about the assumption in the initial state and just monitor it, right? Just run and check, did the initial state actually satisfy the initial conditions, A, right? And then we walk away with this conclusion that the real behavior of the system in the new state must be safe, because we started safe, and by having logic reduce with the lemma and the differential limiting logic proof conducted in the theorem prover, reduces the safety of the system to just the runtime monitoring you've done here, whether the initial state was safe and whether the monitor formula was happy about this transition from the old to the new state as reflected in the old and the new variables. So what we overall do is combine the offline proof parts of the system with the runtime monitoring parts of the system, and because this is simple arithmetic, it's comparatively easy to run compared to evaluating a differential limiting logic problem, which would be technically correct, but is usually a little bit too slow. Now, one slight problem with the approach is still that what if this wasn't the initial state, then checking whether the initial condition was true for it wouldn't be quite the right thing, and what if the model actually is a model that repeats and has a loop? But that's actually a harmless change compared to where we're at. This was generic for any arbitrary hybrid program alpha. Now replace this hybrid program alpha with a hybrid program that is a loop, so alpha star, and the exact same approach works everywhere. And we can become a little bit more precise by saying, well, in that case, actually, the run of the system will have consisted of a number of runs of just a loop body with a number of observations. And we proceed still in the same way. Now with a differential limiting logic proof that always when we start in A, we remain safe after having repeated alpha any number of times. In the only initial state do we check whether the initial condition was true. And then we check each and every one of those transitions, whether the transition from the old state to the new state made the monitor happy, right? Or rather the logical formula that comes out after proof simplifications on this, but that's a minor detail. And then we'll walk away with the conclusion that the state we're at right now also will still have to have been a safe one. And if any of those checks fails, if for example here we discover that that transition was not a good one, not compatible with the model, then we give it an alarm right away and initiate veto fail-safe action. Indeed, that gives us the theorem that the system is safe as long as the monitor is satisfied. And in fact, the system also will always remain safe in all the future behaviors of the model unless one of the monitors failed. Now let's look in a little bit more detail into what happens logically in the proof side in a cartoon sketch. When we ask the proof question, is there a way of running alpha to a state where x equals x plus? And just for emphasis, have I included here the information that this is talking about x, the hybrid program, but it's not talking about x plus, whatever values x plus had, which still stay put. Well, in that case, for example, if this is a system for an aircraft that can either climb or descend, and we now use a logical axiom for it, the one that says there is a way of running a non-deterministic choice to a state where p holds true, which is this here, if and only if there is one way of running it on the left-hand side, or there is a way of running the right-hand side. Okay, let's use this and just split the OR into two separate subformulas. The one where we pursue the climbing and the one where we pursue the descending. And again, recursively, we'll be do proof steps to that until some point in the future, many of those proof steps led to proved subgoals, but some of them did not. And here, for example, F1 did not. That's the logical formula asking about a relation between old and new state. And maybe here we get another one that says, formula F2 that says a relationship of old state to new state is required. And of course, usually You end up with long phases if things don't prove. Here you say, eureka, that's great because we've identified the logical condition on the relation between the old and new state that implies that there is such a behavior of the system. And now we remember in this particular context, there was an or in between the two cases. So of course there will still be an or between those two cases. But in general, you just runtime monitor and fill in the proof at runtime for all the open premises of the proof that you got. And even if those subgoals cannot be proved once ahead of time, they still impose the appropriate assumptions imposed by the model on the relations of the variables, which you simply prove at runtime. So you immediately detect the model violation and can simply mitigate safety issues by going on a safe fallback action instead. Now, let's move on to the question, for typical models that are of the shape control plant repeated, can you do a little bit better by already interfering right after the control run instead of waiting for the entire phase and after the physics run as well? Say, oops, I guess that was bad, maybe we should have interfered earlier. Let's do so. Let's interfere earlier by the controller monitor. But it's sort of the same idea, right? You go from an old state to a new state with a model monitor, which now we understand is often composed of first running a control and then a plant. And already after the control, can you check the real controller's execution from an old state omega to a new state nu? Is that compatible with one of the behaviors that the control model allowed? And we again rephrase this in logic by the question whether the old and new state satisfy the formula that there is a run of the control model to a state where x equals x plus. Again, we do a differential learning logic proof to turn this into simpler logical conditions on the old and the new variables, and then check this at runtime and veto the concrete controller's decision unless it satisfies this formula, which enables us to walk away with the theorem that the controller is safe, and with a little bit more care even in plant bounds, as long as the monitor is satisfied and you can intervene and overwrite the decision right away. This leads to an immediate detection of unsafe control behavior before you actuate it, and so you have perfectly safe execution of unverified implementations, even in perfect environments. Now, speaking of perfect environments, what do you do if the reality is a bit more annoying? Can you somehow predict what the physics behavior will do if you say the model isn't perfect, but maybe it's within certain bounds of physics? What if there's multiple different behaviors that could be braking a little bit harder, a little bit less, steering a little bit more, steering a little bit less? How can all of those be overcome? And of course, Niels Bohr already realized that prediction is very difficult, especially if it's about the future, but we'll try it in any case. So how do we develop such a prediction monitor after a control is run, when a plant is running, but it could have multiple different behaviors, right? In that case, if the ideal world model that we worked with is of the shape differential equation x prime equals f of x within an evolution domain constraint Q, in order to enable such prediction, you need a horizon, so you time trigger it and say, well, okay, reset the clock to time 0, evolve the clock with t prime equals 1, and evolve for at most epsilon time units, so that you need a prediction only for epsilon time units and not forever, because lasting in with a disturbance that holds forever is really hard. And now you move from this ideal world dynamics to something that essentially says, well, I'm not sure this differential equation is perfect. Maybe it's tolerant. Maybe something near it is true. So let's take that in steps. You have a differential equation x prime equals f of x in your model, ideal world dynamics, and then you want to say, well, it's not that, it's sort of like f of x, which is another way of saying, I guess, the derivative of x is f of x plus or minus some disturbance factor delta, or more precisely, the time derivative of x is less or equal f of x plus delta and is bigger or equal f of x minus delta. So it's within a delta range of what the differential equation says. And in that case, can you then again ask a question, what concrete control decision is such that all the behavior of the modified disturbed plant is safe, and do a differential logic proof for that, and then work for a similar safety theorem as before to make sure that the prediction monitors enable even tolerating disturbance, and the guarantee that you detect unsafe control behavior before actuation happens, despite the disturbance that might happen in reality, which enables you to get safety guarantees in realistic environments, even if your safety verification only worked with ideal world models. Of course, it's also possible to instead make the original model much more sophisticated and included straight away in the model, as opposed to by the time the monitor is being built. But sometimes it's easier to focus in on the disturbance merely for monitoring purposes, because at least you already know the concrete control that was running and don't have to work in the generic and abstract anymore. So let's summarize what we've learned today. We've seen Modelplex as the fundamental technique for ensuring that proofs about models transfer to proofs for real cyberphysics systems. And it's the only technique that does this with any proofs of correctness, where we are validating model compliance. We're characterizing the compliance with a model in differential learning logic, just as a diamond modality is useful to exploit the versatility of differential learning logic for different purposes. The proof then transforms this compliance formula into an executable monitor, just with arithmetic, that can be run in a real machine, and with slight twists can even also be run with finite precision machine arithmetic, for example, also in provably correct ways. To overall give you provably correct runtime model validation by combining offline and online proofs, where you first have a model monitor for the question, is it transition from the old state to the new state compatible with the model? Or you can already interfere while the control implementation is running and ask the question with a controller monitor, is this control decision safe before I execute anything at all? And with a prediction monitor, make that compatible even with disturbed planned behavior to say, is there possibly a disturbance that might overcome the safety of the system? If no, then we can run it, and otherwise we may have to act a little bit more conservatively. So overall, meddling with models is an inevitable part of working out the design of a cyberphysical system, but because those models have to include models of reality, it's subtle and difficult to get them right, and Modelplex gives you the once and for all answer to overcome discrepancies and in provably correct way ensure that the safety of your system follows from the safety of the models you've proved offline, along with the safety that you've proved ahead of time about the runtime monitors you're running on the system. Fortunately, the logical foundations of safe model transfer provide a way of exploiting differential learning logic to generate runtime monitors that are accompanied by correctness proofs, implying that if they evaluate to true, then the actual system run fits a provably safe CPS and is thus safe itself. This approach also enables trade-offs that analyze simpler models offline while safeguarding them for suitability with Modelplex monitors at runtime, which overall is a very principled yet pragmatic and useful approach to the safety of real CPSs.